Hi, I'm Shantanu Basu. I'm talking about the mass function of supermassive black holes in the direct collapse scenario. And this is work I've done with my PhD student Arpan Das here at Western University, Canada. If we look at some of the recent observations of high mass quasars being seen at around redshift 7, which have masses over 1 billion solar masses, if you run the clock backward as to their mass growth history, assuming Eddington growth, then if you go back to the redshift of about 20, when these objects are thought to have formed, the seeds are thought to have formed, then the masses need to be at least 10 to the 4 solar masses. And that can be seen even a different way on this slide, where we see that if you start with stellar remnants with initial seed mass of even as high as 100 solar masses, you have only about 500 million years to get to the observed quasars. And so you need a tremendous mass growth in that time, which would require highly super Eddington growth. If, on the other hand, you have something close to even Eddington limited growth, then the hypothetical exponential growth rate of mass, which has a well-known growth time, which can be estimated to be about 50 million years, assuming radiative efficiency of about 0.1 and taking this chi or Eddington factor to be exactly 1, 50 million year growth time gives you about 10 e-folding times within the available 500 million years or so, which is enough to grow by a factor of 10 to the 4. So if you start with 10 to the 5 solar mass seeds, you're in reasonable shape, assuming you can still even get the Eddington growth. So the bottom line is we have a new model with a few simple assumptions that allows us to fit the observed bolometric luminosity distribution of quasars. We're assuming that the luminosities are somehow related to the mass in a linear fashion, as they would be with Eddington limited growth. And here what's shown is the blue dots are bolometric luminosities calculated by Hopkins et al. And the red line is our model. And I'll talk more about the model in the future slides. So what are the ingredients? This is the things I want you to remember. We need basically just 3 assumptions to come up with a plausible model for the mass and luminosity distribution of the quasars. If you start with the DCBH seeds of about 10 to the 5 solar masses, but introduce some kind of initial log normal distribution, and then allow these objects to grow in number during a finite time between 0 and some capital T. And during that finite time, the co-moving number density increases exponentially with a growth rate lambda. In addition, as soon as a black hole is formed, it starts its Eddington limited, or it could even be somewhat super Eddington, mass growth. And that has its own characteristic rate, which we're going to call gamma, and you'll see in a future slide. So put this all together. You have 3 ingredients. You combine them like a good chef. You put it together, you mix it up, and we're not going to go through the math here. The math is available in our paper in AppJ Letters 2019. But the basic idea is if you start with this log normal distribution and every object grows exponentially in mass for a short duration, then the log normal would just shift to the right. But if you have a distribution of lifetimes of growth, because the number density is growing exponentially, meaning that more objects are formed at the end of the growth period than at the beginning, and so more objects have a shorter available growth time till the growth stops. So you're assuming some kind of photoevaporation of the halos at some point, which limits the growth after that time, capital T. So the distribution of lifetimes gives you a power law, and then the finite cutoff, the maximum available time, capital T, actually gives you a truncation in the power law. So bottom line, this is the function that we derived. And again, you can see the paper for the derivation, but basically it transforms some initial log normal into this red line, in which it's not really important what's on the left side, because that's the very faint objects that are not observed. But in this region, we have a power law, and then we have a tapering. And the power law is basically the dimensionless ratio of the 2 different exponential growth rates in the problem. And the tapering parameter is a measure of how many of these mass growth times you have within the available total time of rapid growth of the black holes. So you can extract physical meaning from alpha and beta, And here we've assumed that at the instant that you're observing these objects, if they're bright enough to be seen, they are at that time having something close to Eddington luminosity, which means it's proportional to the mass. So we have a transformation of mass to luminosity. So quickly, from the fit, we can infer a duration of the growth of these objects of about 150 million years, which is consistent with semi-analytic models, and that the rate at which the number density grew was having a characteristic timescale of 28 gigayears. And that's also consistent with some semi-analytic modeling of the growth of DCBH at early times. And we also end up finding that the growth rate is close to Eddington, but slightly super Eddington. So basically, with just 3 basic assumptions, we can understand the power law in the main body of the quasar luminosity function, as well as the truncation to a steeper function, which you would say is not exactly a power law. And what's important really is the breakpoint, which identifies the duration of the population growth era. And as I said, the numbers are consistent with separate estimates of a short duration of growth of the DCBH. Please contact me at this email for more if you have any questions, or look at our paper in the AppJ letters. Thank you.